Space elevators are elevators that would reach up into space and make space travel much cheaper and common. But how would it feel to climb one? As you go up or down a space elevator, there are three forces at play. First is gravity, a downward acceleration that decreases as you climb at a rate of 1 over distance squared. Second is centrifugal force, a weak upward acceleration that increases very slowly as you climb. Finally is the acceleration or deceleration of the elevator car. When the car changes speed, this acceleration is felt. For our first test climb, let's ignore this third force. Imagine that the car can instantly move upward at 300 kilometers per hour and instantly stop. To climb up 35,780 kilometers of track, it would take 5 days. After only the first hour of climbing, you would already feel 10% lighter. This may seem quick, however, you would have already climbed 300 kilometers, 3/4 of the height of the orbit of the ISS. Over the next hours, the net force drops down to 83%, then 77%, then 71%, then 65%, and the sixth hour brings you down to 61%. This descent slows down as you climb because the force of gravity follows the graph of 1 over distance squared. By hour 12, the force has dropped to 41%. When we pass hour 13, the elevator car briefly experiences Martian gravity. The net force keeps dropping, passing lunar gravity on hour 30, a day and a quarter after the climb started. 2 days after the start of the trip, the net force approaches 8%. Past this point, the last 3 days of the trip are done in near weightlessness. Day 3 at 4% gravity, Day 4 at 1.5% gravity, and Day 5, 0% gravity. You are now in orbit. The interesting thing about geostationary orbit is that it isn't counteracting the full force of gravity. Because of its distance from Earth, it is only counteracting 2.3% gravity. For the next test climb, let's assume a constant acceleration then deceleration. This is a much more efficient and quick way to get up the elevator. With an acceleration of 1 Earth gravity half of the way up, and then a deceleration of 1 Earth gravity for the rest of the way up, it would only take 45 minutes to climb the elevator. For the first handful of minutes, the climbing speed is slow. That's how acceleration works. So the net force downward starts off around twice Earth's gravity, because of both the upward acceleration and the gravity from the planet. By minute 5, this double gravity would let up a bit to 177% gravity. At minute 10, the net force downward falls to 141%. This continues downward until 22 minutes and 30 seconds with a net acceleration of 106%. At this point, the whole elevator car is turned on its head. This is because the net acceleration downward is only 6%, while the deceleration is a net force upward equal to 100% the force of gravity. Therefore, everyone would be stuck on the ceiling with a force equal to 94% Earth's gravity. This force slowly increases to 100% over the next 22.5 minutes as net force downward falls to 0. Because of this, the elevator car would need to be adapted so that people could inhabit the floor and ceiling. These are the best two options for climbing the elevator because any more acceleration would not be healthy for the people inside. All in all, climbing a space elevator would be a very interesting experience. It could either be a slow crawl into weightlessness or a quicker ride with a strange perspective flip halfway through.